microprocessor from a standpoint of avoiding too little processor, meaning you can't get the job you want completed, done, or too much processor where you end up wasting space, money, time, things like that. This is more of a chalk talk. In fact, to be honest with you, this is a case where I would prefer to have blackboard and we could just draw circuits and we could write little bits of code and talk about it. The idea is really to encourage somewhat of a back and forth on this. We're going to evaluate choices in terms of ergonomics. And the reason I want to do this in terms of ergonomics and not just simple engineering is because we should consider ergonomics even as amateurs in designing stuff. You build a rig. You build a great rig. QSK, smooth at 30 words a minute, but you can't tune the damn thing. You can't get to the frequency you want. You have to press 6 buttons in order just to turn the volume down or to turn the RF gain up. Well, that's crappy ergonomics. So even in picking something as simple as a little microprocessor chip, we need to have some thought in terms of, okay, for final function, is this going to work for what I need it to do? Do I have anything left over in case I discover I need an additional feature, or if we want to add features? And this is the kind of decision that not only do amateurs make, people in the professional field doing engineering make these decisions. The other reason I came up with ergonomics as a way of looking at it is that I work for a company out of Chicago that has 2 major groups. We do chemical and safety, which is my group. I'm a toxicologist. I do poisons. But we've got another group that does mechanical safety and industrial safety that's mainly interested in ergonomics, how to build a workplace in such a way to be as safe as possible for workers. Because when a worker gets hurt, it costs money. Simple dollars and cents. It costs money. It costs money in terms of getting them medical care. It costs money in terms of them being out of work, possibly being on workers' comp. It costs money to the company in terms of insurance, because insurance doesn't like to pay claims. So ergonomics is an important part of the company I work for, and after talking to an ergonomist a bit over the last few weeks, I've decided maybe I ought to look at this in terms of some ergonomics. So basically there's 3 basic types of microprocessors that we might use. You know, whether it be a small chip like an IC chip, like a PIC chip, or an STM chip like Hans uses in the QDX. You got the small boards, which they're basically, in some cases, they're a PIC chip with a little bit of input-output stuff on it, and maybe voltage regulators, things like that. Or they may be a cut-down version of a large board, like a Raspberry Pi, with limited input-output capabilities, but still a lot more than on a PIC chip. Then, of course, the large board, where you have the greatest flexibility, where you can, in many cases, like in the Raspberry Pi, you can actually download Linux and start with Linux and then add your programs as you want to, where, to be honest with you, with a Raspberry Pi to do a lot of things, the hardware's already there. And in some cases, the software's already there. All you got to do is load it up, figure out how to get Linux to use, how to get the right libraries built into Linux, how to get it to recognize the hardware. And then if you want to be clever, how to build a startup script that'll automatically boot what you want up. You know, in some cases you might slim down Linux, whether it be Ubuntu Mate or whether it be Mint or something like that, into something that's nice and concise and allows for adjustments and maybe additions later on. the full board's, like I said, maximum flexibility, simultaneous programming. You got a lot of complexity for certain uses, maybe too much complexity. If you only need something to act as a keyer that doesn't have memory, do you really need to use a Raspberry Pi? Yeah. The small boards, they offer kind of an in-between. Like I said, some of them are stripped down versions of a large board, like the Raspberry Pi Zero would be a good example of this. Some of them are basically, like some of the Atmel boards, they're basically evaluation boards, which are really small chips, but they got a lot of input, outputs, maybe some control circuits like a joystick or something like that. KD1JV used one of these small boards. He used an Atmel Butterfly to develop a digital SWR meter using an Atmel Butterfly, Stockton bridge, and some to read the voltages and to develop SWR and a watt meter. If I remember right, I remember it would do an SWR, so it could read the two voltages, both the forward voltage and the reverse voltage, and say, okay, oh, this is good. No, this isn't so good, and it would give you an SWR. Complexity can still be an issue with a small board. Again, if all you need is a 6-pin, 8-pin, 12-pin chip, do you really need a board? Sometimes it's a good idea, especially if you're doing a design for yourself or a club project. And you say, well, the club project, you're going to make it more expensive for the club members. Yeah, but that you also then have less issues with construction errors by the end members. Dave discussed that in detail with the QDX. The one thing we're discovering is some of these people can put together the rig, but they can't put it together 100%, and so they don't catch the problem, and worse yet, they don't know how to troubleshoot it. IC chips, limited flexibility, specific functions, but you got to plan. And by planning, you got to plan from a hardware standpoint and from a software standpoint. That too little problem that I mentioned in the title, yeah, that'll bite you in the hindquarters real quickly here. So, too much unneeded complexity. It means that you may have a chip that's only available in a quad pack that you're going to have to somehow get 44 connections to, and you're going to have 50 I/O pins that you're going to have to ground through. You're going to have to ground through a bunch of and then write the program to ignore all those pins. Too little means you have to start over, and it may mean that at least you're going to have to move up to a slightly bigger chip, and you're going to have to add a little bit to your program. Worse means you might have to start with a brand new library and rewrite the entire program. So you want to do this right. And by the way, the manufacturers who make our stuff, they have the same problem. How much can you do with a processor chip? Well, you can do a lot, and if you get it right. If you get it wrong, well, you're not doing too much. Let's talk about people that get it right. WinKeyer. The WinKeyer is, the guts of the WinKeyer is an 8-pin PIC processor, a 12C series processor. Originally it was like a 12C 600 series. He now uses the 12C 840, 8 pins. But K1EL is very clever in how he assigns the input and output, so he gets CW, he gets CW messages. Now that WinKeyer can transmit RIDI, so it can do the FSK or AFSK depending on the transmitter. All that in a real nice little tiny box that with a USB or RS-232 to your computer. Actually, for the new ones, it's all USB. Another group that got it right, Steve and Shell at QRP Works. They use a PIC processor also. And I've had a back and forth with Shell over the last couple of weeks because I was telling him, I said, yeah, I'm going to talk about microprocessors, and I want to talk about the fact that you can get a lot done with a relatively small microprocessor. So the QRP Sidecar series, which is now they have the Extreme, and then they've got the plain Sidecar. The Extreme gives you a lot more flexibility. It gives you a larger screen, 4x20. It gives you the ability to also do ready with it, and I believe PSK31. But guess what? This was originally done for the KX3 and the KX2. And then they said, well, we can do it with the 817. And now they're like, hold on, we can do this with the QCX too. So they have a way to work with Han's QCX, but they found out they're running out of space on the PIC chip. Not necessarily I/O pins. They're running out of space for programming. So they're kind of at a crossroads as to whether to move up in chip size and whether they're going to be able to easily adapt their programming, or whether the next sidecar is a totally different kind of project. So basically what Shell and Steve have done is they've taken a PIC chip and some hardware and some very clever software, and they've basically done the same thing that you would get from a Raspberry Pi 4 and a screen and Linux and a logging program and a simplified version of FLDigi and a keyer, a Win keyer built in there. They've done this with a PIC chip, and it's very clever. But yeah, Shell and Steve they're a little bit concerned because there are a couple of new QRP rigs they would like to be able to have work with the sidecars. The TX500, I don't know if anybody's seen that, but any QRP rig that has a case made out of billet aluminum, is a tough rig. It's water resistant. Basically, it's not just a QRP rig, it's also a lethal weapon. If you hit somebody in the head with it, they're going to feel it. They will go QRT. The other thing is the ICOM IC705. At some point, Shell and Steve are probably going to want to develop compatibility with the ICOM, as well as with the 817, 818, the AZ rigs, and the Elecraft rigs, and the QCX rigs. So this is getting it right, but they don't have any room now to really add. So that's going to be their challenge. That's a neat product. And then guess what? The KX3 uses a PIC chip. The microprocessor is also a PIC. It is not a custom-made processor. The only thing I think that is custom-made in terms of electronics in the KX3 is the screen. Same thing for the PX. The PX3 may not even have a custom screen. That may be a standard 4.3 screen. The KX3, I believe the display is custom made. The rest of it, the microprocessor is just a PIC. It's an 18 series PIC. So if you get it right with these small bugboos, they'll get you where you want to go. Like I said, off the shelf. None of those are, let's face it, Elecraft, they may be the greatest thing since sliced bread, but if they want to sell the rig at less than 10 grand, they're not going to go and get a custom-made microprocessor. And by the way, the PICs on here, that 12F840, that is the PIC chip that's currently in the WinKeyer USB. The 18F, what is that, 18F87K22, guess what that's in? That is in the KX3. You know? Notice there's a big difference between those two chips, yet they do the tasks that K1EL and Elecraft have assigned to them very well. So ergonomically, they're a good chip. Typical uses for these small kits are going to be keyers, frequency monitoring, VFO stabilization. And you say, wait a minute, whoa, how VFO stabilization? How do you do that with a PIC? Very simple. You have the PIC look at a VFO frequency and compare it. And as the VFO frequency moves, the PIC will send a signal to reverse that movement. That's kind of what a huff and puff stabilizer will do. Sometimes it acts as kind of an ersatz phase lock loop. It reads it and says, okay, I'm going to change this a little bit and adjust this. It can do it by simply changing the voltage it puts on a varicap, or changing the voltage it puts on even a rectifier or an LED, because those do have a capacitance associated with it. So that's how VFO stabilization can work with a PIC chip. You know, you say, okay, keyer makes sense. Frequency monitoring, it makes sense. Esoteric use, we might talk as to how a PIC chip can be used to help you point your antenna. We'll talk about that a little later. CW keyer. How many inputs and outputs do you need on a basic CW keyer? Dave says 3.
One output.
Huh?
2 inputs, 1 output.
What if I told you I thought we could do it with 2? Without, I think we can do it with 2, and I'll show you how. In fact, K1EL gave me the idea. But 3 would be the minimum I would recommend. Could you do it with 2? Maybe. We'll see. Can you make it work with 2 I/O pins? Well, we'll talk about it. This is an example chip. And by the way, this is the PIC 12C671 is a chip that's going bye-bye in the next few years. It's being supplemented by the 12F683 series and the 12F840 series.
Oh, yeah.
Simple chip. 2, you got VDD, you know, which is not what you think it is. It's positive voltage to get the thing running. VSS, that's ground. And then you've got 6 chips that can be assigned. You got 6 pins that can be assigned as input, output, clock in or clock out. And as you can see, that'll give you plenty of hardware room to do a lot of things. And here you go. Here's an example circuit. This is the K10 keyer. It is not the current keyer, but as you can see, he's got a setup for commanding multiple messages, for having a speaker, for having an output. And notice he's using a 2N2222 in order to sync a little bit more current and voltage than you can do with just the output of the chip itself. He could have just as easily used 2N7000 and done it between drain and source of the FET. You know, but that's a fairly clever use. And there's enough room to allow you to put 4 messages on there. And if I remember right, for the K10 it allowed 460 character messages. Pretty good for a simple chip. And here you go, now you get to see the chip next to the circuit. and you realize real quickly that 1 and 8 are what you think they are. They're positive and voltage and ground. You look and you go, okay, so what's he doing with the different ones? 5 and 6 are dit and dot paddles. 7 controls which message is going to play, and it also controls the load speed. So that means you can push that button and adjust the speed. You look at 4, and that takes you into program mode, or it can play message 1. And by going into command mode, probably the way it's doing it is if you hold the button down, it goes into command mode. So when you push the button down, it starts the sub function, it times that. And if you hold it down a certain amount, it says, okay, da-da-da-da, and goes into, gives you a P to tell you it's in program mode. The others only will look very quickly and see how much voltage is being read by pin 7, and says, okay, I'm going to play this message. Yeah. So, fairly simple. Programming. For even the most basic CW keyer, you need to have room for boot up. Now some of these chips, that's built in a separate part of the chip, and the 16K or 8K or 4K or whatever they give you, it doesn't include that. It's already there, you don't have to worry about it. But in some cases, it'll tell you, hey, you have to leave this amount for boot up. Then you have to have functions that'll calculate the correct timing for each dash, each dot, the spaces between dashes and dots. You got to have a function you enter the program mode, so you can change the speed, so you can change weighting, because then you have to have functions for that. Now this doesn't even include memories. So this is where we get to the other part of the ergonomics. How much programming space do you need? Can you do this in 2K? Can you do it in 4K? Can you do it in 8K? Well, depends. It depends, because guess what? If your hardware is limited, you have to have a lot more room in your space for programming in order to take out the hardware. So we come back to this question, can you make this happen with only 2 I/O pins?
Yeah.
The answer is yeah. And the K1EL gives you a hint as to how to do it. So what you would do here is one pin would be assigned an out. That would be the pin that you then put into the gate of a 2N7000, so that when it's active, that FET closes down and can sync 5 volts to ground and can key your transmitter. And then the other one is assigned an in, but you have to have more hardware. You have to have a little bit of hardware. You're going to have resistors that then, a resistor package that then, if the PIC chip sees 1 voltage, it says, oh, that's a dash. If it sees another voltage, it says, oh, that's a dot, and gives the appropriately timed signal. So what happens if you press both paddles down at the same time? Can you make this work iambically? The answer is yes, but guess what? You're going to pay the piper in terms of hardware space. What you do is you say, okay, for iambic keying, you say, okay, I'm going to watch for this voltage. And whatever voltage I see, I'm going to open a register and I'm going to assign a value to it. I can assign a value of 0 or a value of 1 or a value of 1.0 or a value of 1.1. You're saying, why more than 2? Why not just assign 0 for dot and 1 for dash? Well, The reason for that is that you want that not to have a value in it at all to begin with. And the easiest way to do it is just say, hey, we're going to add an additional bit, and that way we can have a dot, we can have a dash. And if need be, you can also write your programming in this way by holding, if you hold the key down, it'll count the number of dashes, and then if it gets to, let's say, 12 dashes, which is how an auto alarm used to work, it says, okay, I see 12 dashes, and it sends P back to you and says, okay, we're in program mode. So, you can make a CW keyer work with 2 I/O pins. Question is, do you want to? And the answer is, not if you can help it. You're much better off having separate pins assigned to input for dashes, for dots, a separate pin for what I call the OS, which is the oh shit moment, where all of a sudden this thing is sending crazy stuff, so you can press the button and it automatically reset the keyer and shut down any output, and just so you can do it. But you know, we have some hardware, but you're going to have to use the input for multiple purposes, which means then you're going to have more sub-functions, you're going to have more registers, and you're going to have, you know, basically a software hassle. And by the way, it may also, having all these sub-functions and all these you know, variables that you have to account for, it may also slow the chip up to the point where this chip will work great at 10 words a minute, but suppose you get up to 25. Chip bogs down, doesn't work. So this is where you can get in trouble. This is too little. Yeah. The point is, you're better off starting with a microprocessor with extra pins. And by the way, you have this hassle whether or not it's a simple project or a KX3. I guarantee there are days when Wayne and Eric at Elecraft probably look at the schematics of one of their transceivers and go, if only. I guarantee you Shell and Steve at QRP Works are doing that now, because they've told me they have. Yeah. So that's the end of the presentation. You know, now let's talk about something a little bit more esoteric. So how could you make a PIC processor function to act as a rotator, not as an intended rotator as the programming box? Okay. And how big a chip would you need? Let's just do a little brainstorming about this. How many inputs, outputs? Seems to me that you would want at least 2 outputs. And by the way, remember, with some chips you can assign a chip assign a pin as an output for one function, turn around and assign it as an input for another function. You do not want to do this in cases where you really need always on or always off kind of monitoring. So for this, you say, okay, I got to have 2 output pins, one that can activate a solid state relay to turn a motor left, one that can activate a solid state relay to turn the motor right. Okay, so far we've got the motor turned. What about indication?
You need one analog input.
Exactly. You need an analog input if it's a you need an analog input if it is a high gain or a Cushcraft or something like that. But if it's one of those rotators that uses a reed switch and counts pulses, then you need an input that's digital, and you need a register. You need a variable. in the programming that counts the number, so that when you boot your antenna thing up, it says, okay, hold on, I don't know where this antenna is, and let me go to the non-volatile memory and pull that up. And it says, okay, 987 out of 2860. So let's see, that thing's, since we've got it with south being, that means, okay, it's pointed basically west-northwest. And then it can calculate it and tell you. So you're already up to 3 I/O pins without even having any memories, without doing any measurements. Like, suppose you want to measure the voltage going to the motor. That'd be a wise idea, especially if you've got a large stack. Suppose you want to know exactly where it is real time. Then you have to be able to constantly update that measurement, whether it be of a pot for like a tail twister, or whether it be how many ticks you've got on that reed switch. If it's or an Orion, I knew I'd think of the rotor. If it's an Orion, and you still haven't done any programming for, okay, how do you calibrate it? Do you have enough pins to where you can assign one pin an oh shit function, where you can press it and it just shuts down the rotor, resets the microprocessor, and tells you it needs to be put into calibrate mode. So that's a little bit more esoteric, but that's what we're talking about from picking a microprocessor. So what do? Well, if you're designing something just for you, you pick as much chip as you can handle without having to go crazy. Anything that requires you to ignore a bunch of I/O pins, or that requires that you put a resistor and ground all the pins and then tell the chip that, hey, ignore this, it's grounded, it's too much. But at the same time, you're better off having 3 or 4 more I/O pins than you need. Dave, what's your deal with picking chips for this? You always pick as much chip as you can get, right? Within reason?
Me?
Yeah.
I tend to figure I don't have to use everything, but I'm always better off with more chip than less.
Exactly.
I mean, there are a couple other things. I always worry about what tools are available, because if I get a chip that's a little more expensive, but I can program it faster, or with better tools and better debugging, then I'm better off. My time is worth something, actually. Strange as it may seem.
Yeah, and a lot of the chips that have very few pins often you're screwed both ways. You don't have a lot of pins, and you don't have a lot of memory space for programs.